class here. So under chemical bonding, we're just going to discuss, we're going to dwell much more on the two types of bonding that you learned in chem. We're going to base our focus on the two important types, which is ionic bonding and also the covalent bonding. Yeah, so these are the main ones that we discuss in chemistry. So these two are very important, but we'll be discussing more about covalent bonds because it's the only bond that is a bit unique. So ionic bonding, we know it's always going to exist between a metal and a non-metal, where there is loss and gaining of electrons. Yeah, so the number of electrons lost, so this is between a metal, you know this already, metal and non-metal. Now, my focus is going to be on covalent bonding because under covalent bonding, we're going to break this into two types. So we're going to say we have what we call pi covalent bonds and they're what we call sigma covalent bonds. So pi will be denoted by the symbol for pi, then sigma will be denoted by the symbol for sigma. So there are two types of covalent bonds that we are going to learn. And I'll explain how each one of them is formed, and we'll start with the actual definition of a covalent bond. Remember, you said a covalent bond, you have equal sharing of electrons. That's what we said. Yeah, so there's equal sharing of electrons, and this is always going to be between non-metals, right? This is always between non-metals. That's what we have. And we are going to start with the first one, the simple one, which is just a sigma bond. So all sigma covalent bond can be formed in the following ways. The first one is when you have an s orbital plus another s orbital. So an s orbital is spherical in shape. Let's say there is this guy here. Now this is one s. This is going to combine with another s orbital. Let's call this again 1s. So when these guys combine, one electron is going to be facing up, one is going to be facing down. So you have something that looks like this. This is an s to s sigma bond. This is the first way that a sigma bond can be formed. And remember, we know to say electrons are found in these regions with a higher probability of us locating them, which is called orbitals, right? So now we're saying to form these sigma bonds, we can sometimes be having two s orbitals combining. A typical illustration I can give you is if you're dealing with something that has hydrogen. Let's say an example I can give you is, e.g., I'll give you hydrogen combining with what? Something that has 3 electrons. What has 3 electrons? I think, I don't know, that's I need a non-metal. So let's say there's something that has the configuration of hydrogen is 1s1. Let's say something that has a 3, which is just going to be 1s2, and then you have 2s1, right? So imagine hydrogen combining with this guy. The hydrogen has 1 in the outermost shell. Even this guy has 1 in the outermost shell. So H is contributing 1 electron and X is also contributing 1 electron. So we're just saying the electrons that are being attracted to each other, the ones that are combining, we're trying to stabilize these two. So 1 electron from the hydrogen will combine with the electron in the outermost shell to create a hybrid, which is going to be 1s, and then this is going to be 2s2. So this is what you are going to create because S needs to have a sufficient number of 2 electrons. All I'm saying is the first way that a sigma bond can be formed is when you have an s orbital combining with another s orbital, and this is just an illustration that you can use. So here I just used the X because I needed something that has a configuration that has electrons in S in the outermost shell, because whenever bonding occurs, covalent bonding, we only bond the electrons in the outermost shells to make them stable. Yeah, so this is the first way that you can create a sigma bond. The second way is between an s orbital and a p orbital. So S and P, they can actually combine. So you have one s orbital there with an electron. Then this is going to combine with a sleeping p orbital here with an electron there. So when these guys combine, so we'll just have when they combine, this is going to be this. Then you are going to get the p orbital lying down like this. This is what you'll get. So you have an s and a p orbital. This is a sigma bond as well. So I'm giving you ways that a sigma bond can be formed. So a sigma plus an s orbital and a p orbital can combine to give us a what? A sigma bond. And another way that you can create, the final way that we can create a sigma bond, is when you have what you call a p to p head-on overlap. So this is called a head-on overlap. When you have a p orbital slipping down like this, combining with another p orbital which is down, this can give us a sigma bond. This is just going to be this p orbital. So the answer, when these guys combine, this is simply going to be like that. The two electrons right here, this is a p to p head-on overlap. Yeah, so this we call it a head-on overlap because it's from this lobe to the other lobe, and they're both sleeping on the axis, so they're not standing. So this creates a sigma bond. Then the last type of covalent bond that I didn't mention that we're supposed to go to is the pi. So all pi bonds, pi covalent bonds, are only formed in one way. So this is very easy to remember because this is always formed between a p to p sideways overlap. That's when we create a pi bond. So this, we're just saying there's going to be a p orbital here, and there's also going to be another p orbital there. So there's an electron there and an electron down, an electron there, an electron there. So when these guys combine, so some people would show them to be closely related like this. So some people will say like this, they'll write them like this for you to just see the electrons there. Yeah, but sometimes they don't even get to be close like this. We're just going to see some form of attractions between the top part and also some form of attractions on the down part. So this is a way that can create a pi bond. So this here is what we call a pi bond. It's only created when you have a p to p sideways overlap. That's the only way you create it. In short, the only thing that you can use to remember all this is this following key that I'm going to give you, to say there's always going to be a key in terms of the bonds that you're dealing with. Whenever you see a single bond anywhere, just know you have a sigma bond. Whenever you see a double bond anywhere, just know you have a sigma bond and you have a pi bond. And whenever you see a triple bond, just know you have a sigma bond and you have two pi bonds. Yeah, so this is the maximum that you can ever have. And this can also be related to the type of thing I was explaining last time, to say there's a component which confuses people, which is called hybridization. And I gave you to say hybridization is just a mixing of orbitals, like making a hybrid, right? That's what we just call hybridization. And in a case where you have a single bond, this is mostly going to be due to the sp3 hybridization orbitals. So this is what we call the hybrid orbital that is responsible for that. Whenever you see a double bond, just know it's sp2 hybrid orbital that is present, the one that is very dominant. And whenever you see a triple bond, just know you are dealing with an sp hybrid. So we just said this is when you mix orbitals. So here it simply means you mix one s orbital plus 3p orbitals. That's what's going to create the sp3. Yeah, then here you're simply going to have one s, then plus 2 orbitals. So then the last one, you just have an s and a p orbital. So if I was to give you a structure, all I'm asking of you guys is that whenever you see a single bond, please be reminded of the type of covalent bond that you have to say. You have a sigma covalent bond. Whenever you see a double bond, meaning you have a sigma and a pi covalent bond. So if I was to give you a structure here to say how many pi bonds and sigma bonds do you see in the following structure? So if I was to give you something like this, so this is, let me say, imagine there's a sugar that looks like this from your carbohydrate thing. So if I was to give you to say this is to oxygen, and there is a hydrogen there, you know, to say each carbon needs to have 4 bonds, right? So here you have a hydrogen there, you have a hydrogen there, you have a hydrogen. So according to the key that I've given you guys, if you are following, this is the key that I've given you here. This is the key. How many pi bonds are you able to see in this structure, in this molecule that you have here? How many pi bonds are you able to see here? Esther, how many pi bonds are you able to see? John, how many pi bonds are you able to see here? Are you guys able to hear me? So here, John, we're saying the pi bonds are only going to exist if you have a double bond. So look at the key that I've given you, John. In every single bond, there is, so the key is direct here. So the key, let me give it to you here. So in every single bond, there is a pi bond, a sigma bond. In every double bond, there's a sigma and a pi bond. Then in every triple bond, there is going to be a sigma and 2 pi bonds. So now look at this, John. This guy that you're having here. So how many pi bonds are you able to see here? Okay, so you see that the double bond, there's only one double bond here in the structure here, John. So meaning there's only one pi bond in the whole molecule. Then look at the rest of the bonds. The rest of them are just single bonds. So meaning you just count the single bonds. So I'm going to use, so here you're going to have, so here you have a sigma bond. Here you have a sigma. Here you have a sigma. There's a sigma there. There's a sigma. There's a sigma, there's a sigma, there's a sigma. You have a sigma here, a sigma there. You have a sigma here, you have a sigma here, and you have a pi. So meaning you just have one pi bond. Then how about the sigmas? How many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have 16 sigma bonds. So these are the number of bonds that you have in the molecule. Is this okay, guys? Are you having any questions here? So this is what you'd get in terms of this. Because of our key says in every single bond, there is a sigma. In every double bond, there's a sigma and a pi. In every triple bond, there's a sigma and 2 pi bonds. Is this okay? Yeah, so this is basically what we're having. And any molecule that they will give you, they will either ask you about the sigma or the pi bonds. So these are the two types of covalent bonds that you have. And if you're not being asked about the sigma and the pi bond, meaning they'll ask about the hybridization, and we're just saying whenever there are single bonds that are present, the hybridization is sp3. Whenever there is a double bond, the hybridization is sp2. Whenever there is a triple bond, the hybridization will be sp. This is basically what you'd get. Yeah, and to just re-explain this a bit, you'll find that under sp3 hybridization, of course they'll tell you there's one s and there are 3 p orbitals, and this is calculated in such a way that each one of them is occupying. So you have we're saying this is just going to be 25% of the s character and 75% of the p character. The content of p orbitals is 75 because it's just 1/4 times 100%. Then the content of the p character, there are 3 of them, so that's 3 out of the 4. Then you do your percentage, and then for sp2 you're simply going to have 1 s orbital, and you have this the 2 p orbital. So this will give you 33.3% of the s character, and it will give you 66.7% of the p character. So this is basically what you'd get. Then for sp hybridization, this is obviously 50% of the s character and 50% of the p character, because they are in equal proportions. How we got this 33 is just saying s character is simply 1 out of the 3 times 100%. That's how you get this. Same applies with the p. Yeah, that's how you simply get these percentages. They like asking this when it comes to biology because they would want to know the percentage contribution of each particular orbital in the hybridization. Yeah, so please take note of this. John, are you guys getting what I'm saying? You can check out. I gave proper examples, but here let me just explain using the VSEPR theory, because it's one of the important components you need under this topic. So the Lewis dot structure is a nice structure because it gives us a geometry of the diagram, or a geometry of the molecule. That's what it does. Yeah. So I'll start with an illustration of water, for instance. So you know water is made up of hydrogen, 2 hydrogen atoms and oxygen, right? This is what you have. Now, how do we come up with the illustration, or rather with the shape of water, to say water has a bond angle of 1010, is it 104.9, the one you learn in your biology when you're doing water? So you first of all list all the electrons, the outermost shell electrons. We need the valence electrons. So hydrogen has 1, there are 2 hydrogens, right? Each one has 1 electron in the outermost shell. Then you come to oxygen. Oxygen has 6 electrons in the outermost shell. So this will give us a total of 8 electrons. So bear in mind that's what you have. Then now write the symbols of these 2 elements that make up water. So put oxygen on the middle, and put hydrogen this side, and also put hydrogen this side. So hydrogen needs 2 electrons for it to be happy. So meaning I'll put 2 electrons here. Even this guy needs 2 electrons for it to be happy. I'll put 2 electrons there, and also put 2 electrons there. Then I'll simply write something like this. Then you know to say the reason why we're putting oxygen on the middle is because oxygen can accommodate more than it needs 2 electrons for it to be happy, right? That's what we're basically saying. So this is what we have, and because it can accommodate a lot of 2 electrons, it needs 8 for it to be happy. So remember, from the 8 electrons we've only used 4 so far, so we need to put the other 2 electrons here. So put the other 2 there, then the other 2, put them down. So this is what we have at the beginning. Hope this is okay so far. Then from here, we're simply going to represent the shared electrons with a line. So if there are 2 shared electrons, you're going to represent them with a line. If there were 4, we represent them with double lines. If there were 6, you represent them with 3 lines. So here there's just 2, so we're just going to say H is equal to that. Then this is going to be formed. So hope you are okay with the transition we've made here. This is what you have. Then from here, we simply bring the electrons closer to each other. So these electrons here, the electrons participating in the bonding, these are called bonding electrons. These are bonding electrons. These ones here that are outside, that are just left on the oxygen, on the central atom, these are called lone electrons because they are not participating in the bonding. So now we get these lone pairs and bring them close to each other. So close to each other like this, so that they repel each other in advance, because we don't want them to later on have any repulsion forces between them. So we make them deal with each other at the beginning, so they will repel each other very much, and when they repel each other, they will cause the bonding pairs or these bonds to also move. That's how the bonds for water bend like this. And once they do bend, that's where we get that angle, the 104.9, to say this is the actual molecular shape of water. And now we say the shape of water is that some people say it's V-shaped. If you are looking at it from this side, it looks like a V, right? Or rather, some people just say it's a bent structure. It bent because it was supposed to be a linear molecule, but because of the lone pairs on top, it has been bent. That's basically what you have. So there are rules that can be guiding us to be getting the correct molecular geometry, to identify correct geometry. I'll send the list in the group. It's just like a periodic table. Yeah. So once you identify the number of atoms attached to the central atom, and also the lone pairs on top of that, central atom, you'll be able to get the name. Yeah, so there are so many names that you're going to be using. So some of them as follows. Let me just give you the common ones that you have to know. Yeah, so the common one you have to know is how a tetrahedral is formed. You have to know this. The other one is when a trigonal planar. So this is when a trigonal planar is formed. You have to know this. Yeah, so the other one is trigonal bipyramidal. Yeah, so you need to know these. These are the common ones. So I'll send the list in the group. Yeah, so this is basically what you need in terms of the structures, and the Lewis structure diagrams. I will send the same video I once sent. It will help you to be able to look at other examples. Yeah, because things like, for example, if I give you to say what's a Lewis structure of ammonia, this guy here, ammonia, I'll say 4 with a positive there. So the number of electrons that we're having here, initially, without considering the charge, you are supposed to have 5 from the nitrogen, then 4 times 1 from the 4 hydrogens. This is supposed to give you 9, right? But there's a positive here, meaning 1 electron was deducted. This is just going to be 8 electrons. So if you're dealing with 8 electrons, you already know to say you have to make the hydrogens happy. So these hydrogens needs to be happy, meaning 2 will be pushed there, meaning you have 1 hydrogen and 1 hydrogen. Then there's a lone pair there. The lone pair will repel these 2 guys. So this is going to be the lone pair there pushes the other hydrogens a bit on the sides. Then the other hydrogen is down there. So this has given us the shape for the ammonia ion. Yeah, so hope this will help a bit to understand what was talked about in the in the recorded video that I once shared. Yeah, so if there are no questions here, let me just make a recording for the tutorial sheet 4 for math for 1100 and the quiz that Mapalo had asked in the group. Then yeah, we'll be able to interact on WhatsApp unless if there are any questions here. Mavis, where are you guys in class? In chemistry? Oh, okay. Okay. All right.